I think you should be our class rep. Be taking attendance.
Okay, we should take attendance.
Yes. I have attendance of the previous one, and we can see it on the video. But let's start taking attendance from now.
Okay, I think we can just maybe chat our maybe names.
No, you will see it. When people sign in, there is a way you can.
Okay, let's start. This is the module 4, which is the physical layer. I have also sent this material I've sent 5, 6 as well, so that you have a complete module for the exam. That's the next module exam. And then I've equally sent 7, 8, 9. Also, for those of you who will be preparing over the weekend against the subsequent module exams. So you can do well to go through the material ahead. I think that will really help. This is the physical layer we're looking at. And under the physical layer, we'll basically be looking at the purpose and function of the physical layer. In the network, we'll look at the characteristics of the physical layer. We look at the basic characteristics of copper cabling, explain how UTP cable is used in Ethernet networks, and then describe fiber optic cabling and its main advantages over other media. Connect devices using wired and wireless media. The purpose of the physical layer, if you look at the OSI model, you agree with me that the physical layer is the cable, the hub. So hub is also an example of physical layer. And at that point, what you have is actually bits of zeros and ones that have been transmitted from one point to the other of the cable. So the physical layer transmit bits across the network media, accept a complete frame from the data link layer. That is, above the physical layer is the data link layer. And this is the last step in the encapsulation process. So if you remember vividly when we're talking about the OSI model, we did say that starting from the application layer downward, the next layer before the physical layer is data link layer. So here, we're trying to tell you the characteristics of the physical layer. And it accepts a complete frame. Remember, at the data link layer, what you have is frame. So the PDU of data at the data link layer is frame. And that is what is being received by the layer 1. So this is the last step in the encapsulation process, which is the bit. Remember, the first is data, second is a segment, the third is packet, and the last one is bit. So the PDU of data at the physical layer is bit, and PDU means protocol data unit. The next device in the path to this destination receives the bit and re-encapsulates the frame, then decide what to do with the frame. So invariably, these are the characteristics of the physical layer. Going further with this, you can see the physical layer here. And the physical layer standards are implemented in hardware and are governed by many organizations, including the ISO, the EIATI. These are different, all the bodies that regulate the physical layer. And also here, you have physical layer standard address 3 functional areas, which is physical component, encoding, and signaling. When we talk about the physical component, of course, you agree with me that your wire is part of the physical component, and the encoding process is the format of the signals. So you know too well that these signals are actually, there's some kind of variation. For copper, the behavior of the signal is different. Under signaling, of course, I've told us that the encoding is broken down of these bits itself. But for the signaling, if you look at copper signal, it's quite different from that of fiber optic cable. The fiber optic cable is that of light. So as we go further, I'll show us under, I think that should come under Ethernet. So we're going to look at the different signaling behavior. But one thing I'll let you understand here is that what you have for copper is different from what you have for fiber. So look at the encoding. Encoding converts a stream of bits into a format recognized by the next device in the network layer. So this encoding, this coding provides predictable patterns that can be recognized by the next device. Example of encoding method include the Manchester shown in figure. That's what you can see here in the figure. So this is to give us a different encoding patterns when it comes to the physical layer. So we have different encoding methods. The one here is the one which is that of the Manchester. So if you see here, when it's 0, it's actually down. When it's up here, it is 1. And then you go on and on. So you could see that you're actually operating from half, that's midway of this 0 line. And then same thing when it's going up. So this same behavior is tagged as Manchester method of encoding. And then look at this also here for the signaling. Good enough, we have this. So you can see that of light, which is where the fiber optic is. And then the signaling method is how the bits of values of 1s and 0 that are presented at the physical medium. Remember, we said at the physical layer, what you have is bits of 0s and 1s. So the method of signaling will vary based on the type of the medium being used. Like what you have is a microwave signal over the wireless signals. So you can see that here. And then for electrical signal over copper, you can also see, so there's variation in the pattern itself. Then bandwidth, what is bandwidth? Bandwidth is the capacity at which a medium can carry data. So digital bandwidth measures the amount of data that can flow from one place to another in a given amount of time. So your data, your bandwidth has to do with the capacity of which you can have, the capacity of transmission of this data itself. So it's like somebody say, what's your bandwidth size? You know, you could say, oh, we're operating at 1 Mbps, 1/2, or sometimes you say, oh, we're on 1 STN and all of that. So all those, these are data sizes, that's transmission of data, the capacity of what you've been given, either from the ISP or whatever. And remember, it is measured in bits per second. And then you can graduate it to terabytes per second. So you can see when it's bit, it's actually the least. And then when it's kilobit, it is 1000. In some cases, it's 1024. But then when you explain it in the class like this, you don't need to start giving those technical values. So you could just summarize it as 1000 kbps. And then same thing for megabyte, it's 1 million. And then for gigabyte, you can see here, that is 1 billion, that's 10 to the power of 9. And then for terabyte, terabit is in 10 to the power of 12. So you can see here is a multiple of 1000. So that's actually the capacity of which the bandwidth is being rated. Then bandwidth has terminology like latency. You need to explain to your student what latency is. Of course, when you're transmitting data, there's latency. The amount of time, including delays for data to travel from one given point to another, is referred to as latency, which also can be measured. Then throughput means the measure of the transfer of bits across the media over a given period of time is referred to as throughput. Throughput is the measure of the transfer of bits, transfer of the signal over a given period. Particular time is throughput. Then goodput is a measure of usable data transfer over a given period of time. So when you say throughput minus traffic overhead, it gives you what? Goodput. So these are more or less like a kind of a small calculation here. But remember that the good put itself is when you're looking at the usable data transfer over a gift. So that means you're not looking at the overall size of the data, but rather you're looking at the usable one. So that means when you minus the traffic overhead from your throughput, you get good put. And the throughput is the actual measurement of the entire capacity yourself of that bandwidth. So that means then what the entire network can carry up. When you say, oh, we've actually optimized our network to the peak, for instance, it means that you're actually operating at the highest throughput value. So we're saying when you manage that overhead from that actual transmission of data for that network, you get the good put, which is actually the main usable data on the network. Okay. So copper cabling, this actually requires some kind of crimping of cabling, which also can be done in the lab. But we also look here, we'll look at the configuration as we go on. So at the color coding, you can be able to get used to them. The copper cabling is the most common type of cabling used in networks today. It's inexpensive, easy to install, and has low resistance to electrical current flow. The limitation you could have with that is attenuation. The longer the electrical signals have to travel, the weaker they get. And that is the reason why when you start running copper cable and you get to 70 meters, thereabout to 100 meters, you have to discontinue that connection by putting a repeater station or a switch to be able to regenerate that signal. If you continue to run copper beyond 70 to 100 meters, you're bound to experience attenuation. So attenuation is the loss of that signals over that long distance. So it is best that once the distance is above 70 to 100 meters, you either use a copper, you either at that point in time use fiber optic, or you put in a new switch and then reconnect from that switch so that you can be able to regenerate the signals. Electrical signals is susceptible to interference from two sources, which can distort and corrupt the data signal: electromagnetic interference and radio frequency interference and crosstalk. These are actually interferences that actually affect copper cable. So for instance, if you have your data cable running side by side with power signal, you're meant to have this kind of interference. So it is best you run them separately to avoid interferences, and then you could have radio interferences in most cases. So these are things to be avoided. Then mitigation, strict adherence to cable length limit will mitigate attenuation. There is need to adhere to cable limit so that you can be able to avoid attenuation. Like we said, within the range of 70 to 100 meters, you should be able to terminate a new switch, as the case may be, and then run it up from there. So some kind of copper cable mitigate EMI and RFI by using metallic shielding and grounding. And some kind of copper cable mitigate crosstalk by twisting opposing circuit pair wires. So when it's being twisted, it helps to take care of crosstalk. So we can see types of cabling of copper cabling here: unshielded and the shielded type. The unshielded type does not have the shield around it, while the shielded twisted pair has this shield you can see around it here. And here below is what the cozier cable. This cozier cable actually used at the back of our TV for simplest connection. And then you also have it for your VSAT, and even the modem also uses cozier cable. So for the unshielded, is the most common networking media terminated with RJ45 connectors. Like you can see in your lab, at least when I was in your place last time, I actually saw that So it would be nice some of the instructors visit the lab to be able to see this. So, Sir Julius, I think you help me play that role over there so that they can be able to see
I will.
The cable and possibly crimp the cable themselves because they are now instructors. And
Yes.
then, I mean, practice over and over. So you need to allow them to use it so that when they are teaching the student, it will come really handy for them. So key characteristic of the UTP is that the outer jacket protects the copper, but I think this is best when you see them yourself. So please just let them see it so that the too much grammar here can be narrowed down.
So when you come to the network lab in Block D, we have everything there.
Oh, lovely, lovely, lovely. So please, I would advise that all the instructors, those who haven't done hands-on in this area, should use the lab so that before you take this model exam, you'll have, practice that aspect. Okay, so the twisted pair protect the signal from interference, and the color code plastic insulation electrically isolate the wires from each other and identify each pair. So that's the reason why you have it isolated, to be able to help identify each pair of the cable, so that when you're using white, blue, this is blue, white. You're using white, brown, that there are different colors. So, of course, I'm going to tell us the color codes while you do the practice in the lab. For the shielded twisted pair, better noise protection than UTP, more expensive than the UTP, harder to install than UTP because it's quite hard, terminated with RJ45 connectors, interconnect host with intermediary network devices. Of course, all of them does that. Key characteristics of the STP, which is a shielded twisted pair. The outer jacket protects the copper. Okay, and then the braided or fuel shield provides EMI and RFI protection. So remember, we said the EMI is electromagnetic interference and the radio frequency interference. So once you use the STP, you're sure that you can be protected from that. And the fuel sheet for each pair of wires provide the EMI and the RFI protection. So the color-coded plastic insulation electrically isolates the wires from each other and identify each pair. So it's actually for isolation and for identification. And here is a coaxial cable. I strongly want to believe that most of us actually have seen this coaxial cable, probably behind our DSTV dish or at the VSAT. Also might have seen it behind the TV in most cases. So this is also, it consists of the following: outer cable jacket to prevent minor physical damage. That's why you can see the outer cable quite thick, thickened somehow. And removing copper braid or metallic foil act as a second wire in the circuit and as a shield for the inner conductor. So you can see even from the picture, I think we can actually relate it to what I'm saying here. So a layer of flexible plastic insulation and then a copper conductor is used to transmit the electricity signal, which is number 4 here. So each number here is meant to be tied to what you're seeing here in the diagram. Now, there are different types of connector used with the coaxial cable. So you can see the different, we have the BNC, the N-type, and all this depends on whichever device you have. Of course, their port has different variations. So you need to look at the right connector that will match with that port. So let's look at the cabling itself. So if you see here, we have 4 pair of cable. So let's see what happened here. The cabling standard actually is the TIA EIA. We have it, the TIA 568A and the 568B. So it's either you're using type A or you're using type B. When we look at the way these cables are being structured, we have it from category 3, category 5, and 5E, and category 6. We now also have category 7 and all of that. The category E, like I said, is the one used for telephony, which is actually 2 pair. The category 5 is, I think, came after category T and 3. And the 5E here is enhanced. So we have a category 5 enhanced cable. And then we have the category 6. I think the last class, I think the first class, we actually looked at the differences across these cables, so that when you're talking about category 3 cable, category 5 cable, you know what that means. And so you can see from category 3, you have just 2 pair. So this is the connector for the RJ45. And like I said, we have the T568A and the T568B. This is actually for a straight through. So your straight through cable can either be type A or type B. And let's see the color code from this diagram here. Also, you can see the color code in here. For the type A is white, blue, blue. So Julius, I hope you can follow here so that they can use this slide to look at the cable and match it. White, blue, blue, white,
orange.
Yeah, white, orange, blue, and then white, blue, orange, and then white, brown, brown.
White, brown.
Now, once they arrange it in this order, is type A. When they arrange it in this order, is also type B. It means that you can choose to use a type A or use a type B. That means at the both end of the cable, you maintain the same convention. But if you choose to put type A at one end and type B at the other end of the cable, automatically becomes a crossover cable. So that's what's the difference between a crossover and a straight through cable. It means that at what point you're using. So, and when it's a straight through cable, you connect it host to network devices. And when it's a crossover cable, host to host, switch to switch, router to router. So in case you're asking yourself, at what point do I use straight through cable? At another point, at what time do I use the crossover cable? So it's also stated here. But as we go on, you also see there's what we call the auto NDI, which actually is the modern way that most of these Ethernet ports have been configured, such that they could work with both straight through and crossover. I remember far back then, in the early 2000s or late 90s, you must know when to use a crossover and when to use a straight through. But today, we see ourselves using crossover straight through without any issue. But far back then, if you use crossover to connect, maybe you want to connect system to system, 2 systems together, and then you use a straight through cable, is not going to work. You must use a crossover for system to system connection. Okay, so this is a fiber optic. The properties of a fiber optic cable is that not as common as UTP because of the expense involved. Quite expensive, ideal for some networking scenarios, especially when the distance is high, and then transmit data over long distance at high bandwidth. So in other words, when you have connections beyond, in some cases they'll tell you above 500 meters, you have to use fiber optic. Fiber optic is advised to use at that point in time. Reason being to avoid losses. Of course, if you use radio, you're going to also encounter losses. The only medium that helps you to eradicate losses is fiber optic. Every other one, for some reasons, you must encounter some kind of losses. So less susceptible to attenuation and complexity, immune to EMI and RFI. Made of flexible, extremely thin strands of very pure glass. Uses a laser or LED to encode bit as pulse of light. So the fiber optic cable acts as a waveguide to transmit light between the 2 ends with minimal signal loss. It means, like we said, is the speed of light it uses. So that means you expect it to verify. So we have 2 types of fiber optic cable. It's either the single mode or the multi-mode. So when you are doing connection for long distance, you're looking at using the single mode. That helps you. Then within the building itself, you use the multi-mode. So for long distance application, use this. And then for up to maybe 10 gigabyte per second to 500 meters, or probably for internet kind of setup within the organization, you can use the multi-mode. So dispersion refers to the spreading out of a light pulse over time. Increased dispersion means increased loss of signal strength. And then the MMF has greater dispersion than SMF, which is called the multi-mode fiber and the single mode fiber, with a minimum cable distance of, for MMF, which is 550 meters. So they're trying to let you know that this is the distance in which is advisable it is used. There are questions that will come up that you see, and telling you if you have to maybe 2 buildings apart and they're 500 meters away or even more, what kind of medium would be advisable to be used in that kind of situation. So you just have, please, when you're reading, read to look at it from an application point of view, not just reading to just understand these terms, but also to see how you can apply them, because these are like practical things to be done. Because of course, this we expect at the end of the CCNA1 to 3, the students have actually acquired the right knowledge to be able to go out to the industry and then begin to use them. So the fiber optic cabling is now being used in 4 types of industry. The enterprise network is also fiber to the home, and then long haul network, which is used by service provider to connect countries and cities, just like what Glo also did. Submarine cable network used to provide reliable high speed, high capacity solution capable of surviving harsh on the sea environment at up to transoceanic distance. Our focus in this course is the use of fiber within the enterprise, as within the organization. So these are some of the connectors you see in the course of terminating fiber within the organization. You're using the straight tip, that's the ST connectors. We're using the lucent connectors, the duplex mode connectors. All these has to do with the port itself. So they come in different, so when this fiber has been spliced, it's been spliced using the different connector types you can see here. Okay. But please, this is for the multi-mode, which is within the organization. Like we said earlier, we look where our major concern is the type used within the enterprise. So fiber versus copper. I don't think we should put fiber side by side with copper, because the advantages you have with fiber is higher compared to that which you have on copper. So, but if you look at it, you can see that everything here on fiber is high, as against low in copper. So that tells you that there are high advantages or high benefits in using fiber over copper. So the wireless media, properties of wireless media, it carries electromagnetic signals representing binary digits using radio or microwave signals. This provides the greatest mobility option. Wireless connection numbers continue to increase because of the flexibility. Before now, everything has been on wired. Most of us actually knew what we suffered using wire. So anywhere you go, you have to connect cable for you to browse. You know, but today, wireless is the order of the day, in as much as a lot of security vulnerabilities when it comes to wireless network. So some of the limitations of wireless is coverage area. Effective coverage can be significantly impacted by the physical characteristics of the deployment location. Interference is high. Wireless is susceptible to interference and can be disrupted by many common devices. Security, a lot of security issues, and then shared medium. So wireless operates in half duplex, which means only one device can send or receive at a time. Many users accessing the wireless LAN simultaneously result in reducing the bandwidth for each other. So you discover that the more users you have, but the good thing here is that the wireless technology has been improved upon. So we expect to see, that's why you're seeing it from 802.11a, you have B, you have G, you have N, you have CN, and all of that. These are the standards given to us by IEEE. Just let us know that the throughput of the wireless network has been increased over time. So I think most of the challenges have been taken care of in terms of the capacity of data that can be transmitted over your Wi-Fi, which is a wireless network here. So types of wireless media, the IEEE and the telecommunications industry standard for wireless data communications cover both the data link and the physical layers. In each of these standard physical layer specifications dictate that data to radio signals encoding method, frequency and power transmission. So look at signal reception and decoding requirement, antenna design and construction. So this is the requirement here for the wireless media itself. So the standard is that for the 802.11 wireless LAN, so for your wireless LAN, you're looking at 802.11. So you might have different, this is like a generic. So you could have 11A, you can have 11B. I think the subsequent slide, we also see that as well. Then for your Bluetooth operates at 802.15, which is actually used for personal area network. And remember, personal area network is just a setup of your system connecting with maybe Bluetooth connection to your printer, your scanner, because everything is going wireless. So you could have a workstation in your office that is connected by Bluetooth, and you can print and connect, share resources and all of that. So it's referred to as a PAN or wireless PAN, as the case may be. So for the wireless, we're looking at you using Bluetooth. WiMAX is 802.16. This is like your glow matched and all of that. They fall under the WiMAX. And use a point to multi-point topology to provide broadband wireless access. And then the ZigBee, which is 802.15.4, is for low data rate, low power consumption communications, and primarily for Internet of Things, that's IoT. And remember, for your IoT, you're looking at even some of your cameras, they actually operate on the IoT and all of that. Okay, so those are the standards we have. And then in general, a wireless LAN requires the following devices. That's your wireless access point, which concentrate wireless signals from users and connect to the existing copper-based network infrastructure. So you can, I think I also saw that also in that office, you have a wireless access point that, of course, you must connect it via your existing network infrastructure. The wireless NIC adapters provide wireless communication capability to network hosts. So on the same wireless access point, you have a NIC, and that NIC is what actually provides that capability. So there are a number of wireless LAN standards. So when purchasing wireless LAN equipment, ensure compatibility and interoperability. It's compatible, and then it can operate. So network administrator must develop and apply stringent security policies and processes to protect wireless LAN from unauthorized access and damage. So you could do maybe MAC filtering. You could do, you could actually increase the security of the network from 64-bit to maybe 128-bit encryption. That's wired encryption. You can do all of that just to see how you can beef the security for the wireless. There's a packet tracer to connect a wired and wireless network. I think what I will do in the next class, prior before I start the next class, I'm going to do some practicals again to bring up those devices, and then we can play around it. So I think I was going to do that, but today is taking almost 1 hour of our time, but by Monday, I'm sure to do a 1 hour lab before moving into the class proper. Is that okay by us, Julius?
That should be okay.
It's not there.
I'm here. I'm with you.
Yes, I'm trying to say that as we go on in this course, I will be interfering with lab activity, maybe 45 minutes, then I continue with
that will be fine.
Because I want to see that I touch these lab activities for every class, add new things for you guys to see the much you could do with the packet tracer at this level before you start applying routing protocols. Because even in this CCNA1, you also meant to do some routing protocols. So I think it will be best before every, at least if you have 2 hours, we could use like 1 hour or 45 minutes for the lab, and then we move on.
I think the lab will be nice if we use like 1 hour for the lab. Others, when we are reading, we will get it better.
Oh, lovely, lovely, lovely. So I think I also support that. So the rest of us, are we okay with that?
That's okay.
Okay, fine. I think that will go a long way. Number systems. The much talking we do here is CCNA1, because that is where the theoretical background of the course is. But as you move on to CCNA2, most of them actually lab, most of the things you do actually are lab oriented. So module 5 is number system. And this numbering system, we're looking at this normal bits of 1 zeros for your IPv4 and IPv6. Looking at the objective is to calculate numbers between decimal and binary systems, calculate number between decimal and hexadecimal. And so here, actually this area touches more on your IPv4 and IPv6. Okay, so binary number system consists of 1s and 0s called bits, and a decimal number system consists of 0s through 9. And then your host servers and network equipment using binary addressing to identify each other, which is the IPv4, like we said before now, is 32 bits, divided into 4 strings or 4 sections called octet. And of course, when we say octet, the bits of 1s and 0 all combined, not beyond 8. So once you have 8 bits, it's a dot. So each octet contains 8 bits separated by a dot. So the entire length of an IPv4 is 32 bits. But after every 8 bits, there's a dot. And if you convert that 8 bits of zeros and ones to decimal, you now have numbers like maybe 120, 130, 140, which you now have to categorize into the different blocks of class A, B, C, D, and E. Okay, so let's go on and see how these numbers are actually structured. I think this approach here is just to let you know, okay, position of number, if you have 3 is 10 to the power of 3, for 2 is 10 to the power of 2, and for 1 is 10 to the power of 1, and if it is 0 is 10 to the power of zeros. Let me see the one that will make it more handy for us. Okay. If I have, for instance, 0, 0, 0, 0, 0, like this number now, you have a binary number of 1, 1, 0, 0, 0, 0, 0, 0, 0. If somebody asks you now, how many bits are here? If you count, you have 1, 2, 3, 4, 5, 6, 7, 8. Good. That's an octet. That's the octet you're talking about. Now, this octet, if you're asked to convert it from binary to decimal, of course, if some of us could recall, we were taught in secondary school, binary to decimal and all of that. So this is where you now apply it in the real series and make it practical. So it means that when the signal is active, like 1, you look at the decimal equivalent. So if you start counting from here, what we're saying is that this is 1, 2, 4, 8, 16, 32, 64. How did we get this? It means 2 times 1 to the power of what? 0, isn't it? Because you're meant to start from 0. So
Yes.
you take this one, you say 2 times 2 times 0 times 1 to the power of 0 and all of that. So this, like this first one is 1 times 2 to the power of 7. This one is 1 times 2 to the power of what? 6. 1 times 2 to the power of 5. That's 0 times 2 to the power of 5. 0 times 2 to the power of what? 4. 0 times 2 to the power of what? 3.
8.
0 times 2 to the power of 2. Then 0 times 2 to the power of 1. Then 0 times 2 to the power of what? 0.
Yeah.
But you know, when 0 is multiplying everything is what? 0.
0.
Yes. So when we say 1 times 2 to the power of 7. So 2 to the power of 7 gives you 128.
128.
So it means that anytime you have 1, 1, those are the 2 active numbers. You will be less concerned with the other zeros because it will cancel out. So you look at what's the equivalent, decimal equivalent value on top of it. When you add the 2, you have the decimal equivalent. So in this case, what I have up here is 128. What I have here is what? 64. So I don't know if I can quickly just give us number now so that some of us will try it and see. So if we said for the entire length of octet is usually from 128 to 1. So if I give you another number that says 111, that's 111. Somebody can try that and tell me what the answer is. And then you have the remaining ones as zeros. What would be the decimal equivalent? Anybody there? Nobody? Who can help us? Here is 1, 1, and then all zeros. The remaining 6 bits are all zeros. The decimal equivalent is 190.
How many ones?
Here we have 1, 1, 1, and then the
Okay.
remaining zero, the remaining bits are all zeros, which is
That's 224.
Thank you very much. So it means that if you're converting 111 00000 to decimal is 224. So that's how we do the conversion. So if I ask you now to convert 1101 then 000 to decimal, what would be the value?
1101
01 and 0.
192 plus
232.
Who can tell us what's the answer?
208.
232.
Are you sure?
208.
208.
It should be
11101.
I will leave it 208.
So that's 192
You
plus
said you have
16.
311 01
208.
This 321.
We have
This
311 01
3101.
Okay.
When we have
311.
311, you say 222.
232.
Now why 208?
Yeah. Plus
So who will help out?
232.
224 plus.
232.
Thank you very much. 232. So it is 232. So you can see this is how you do the conversion. Reason being that for the triple ones, which is already 224, like you said, Esther, earlier, then the next one is what? 0. It means to cancel out. Then the fifth bit here is 1, and on top of 1 is what? 8.
8.
Good. So you now have 224 plus what? 8, and you get 232. So that's how you quickly calculate this number. Are you okay with that?
Yes, I understand it. I didn't know you said 321. I thought you said 1101.
No,
That's
I said
weird.
341.
I understand. Thank you, sir.
Okay. So this is how we do this conversion, and then you could get so even with all these things you see, don't get confused, please. Your major focus is you look at the bits of ones and the bits of zeros, and then look at the one that's active and take the decimal equivalent, add it up, and you get your decimal values. And that's exactly what you do with the others. So don't let all these be big numbers, multiplication here gets you confused. The point is that once you're giving, like for instance, you're giving 000, 1001, you can say 010, and you're asked to convert it. So you know that all this from here down will be cancelled, isn't it? Then this one that is 1 is active, on top of it is what? 8. And then this is what? 2. So when you add it, what do you get?
10.
10.
Yeah, you get 10. So that's exactly how you do the numbering. So that makes it a lot easier for you. So you don't need to bother yourself. So if you're giving this, so if you look at what we have here, this is 192.168.11.10. How did we arrive with this? They are telling you that the first octet is this first one, which is 192. The second octet is this one. The third octet is this one. The last octet is one. So if you add all these bits together, you have 32 bits put together. So look at it here. They're trying to convert 110000.10. Are you seeing it up here? Now, when you do all this conversion, you get 192.168.11. This is something you also practice on your own and see. So that's decimal to binary. So please, we need to do a lot of practice with this and then be able to show it to our student. It will come a little bit. Hexadecimal is quite simple. It's even a lot easier than. So for decimal, we know you're counting. For hexadecimal, you're counting from 0 to 15. That is hex 16. So if you count from 0 to 15, you have 16 bits. Here, it's telling you that it was the binary equivalent. For 0, it is 000. For 1, it's 001. So what do? You count, you take 8 zeros, 8 ones. The next one will be 4 zeros, 4 ones, 4 zeros, 4 ones. Then the next one will be 2 0, 1 1, 0 0. Some of us teach this, Abby. Am I correct?
Yes.
So, and then 0 1 0 1. So once you take it across, this is the
Value.
the value you get. And then once it is 9, it is 1 0 1. And then once you go beyond 9, the next one is 10. 10 is A, and then 11 is B. So that's where the IPv6 comes in, and that's why in the IPv6 you could see 08ADB, F. What we're saying is that if you're going to expand it to the bit itself, you're going to have, let's say, let me just ask this class, for instance. If I give you 0, A, B, 8, A, B, who can tell me what that represents? 0, 8, A, B. What do you have?
0, 8, A, B.
So the 0 is what? 4 zeros, isn't it?
Yes.
Then the 8 is what? From what you can see here, 8 is what?
1 0 0.
1 0 0 0. Good. And then the A is what?
1 0 1 0.
And then the B is what?
1 0 1 1.
Thank you very much. So by the time you add all those bits together, you are going to have 16 bits, and that is what is called hextent. So the 08AB is an hextent. You don't put column, and then you have another number again, arbitrarily assigned in that manner. But the point we're saying is that it must be within 0 to 15, which is F. So you're not going to have a G, you're not going to have a H, but everything must be within that range. So for every hextent, when you break it down into the binary bit itself, if you count it, you get 16 bits. I don't know if we're clear with that. So this is what we're saying in excess here. This is 0. Are we saying it?
Yes.
Are we following?
Yes.
Yes.
They are telling you that the minimum for hexadecimal is 0000, and it will increase to FFF. FFF means at this point is 15, 15, 15. Are we together?
And that's 1 1 1 1.
Exactly. That is 1 1 1 1. Now the same thing, minimum 000 1 1 000 1 1. Because if you go back to check what 15 is here, 15 is 1 1 1. Agreed?
Yes.
Good. So that tells you that your minimum is all zeros, your maximum is all F. And you can see separated with a column. And then the fourth here, we took this fourth one here and further break it down. So you bring out the 0, you bring out all the 0 bits, and then you have it. So if you count it, you're going to have 16. So 4 hexadecimal digit is equals to 16 binary digit. Is it clear?
Yes.
And if you count everything together, you're going to have 128 bits. Yeah. So if you count all this F now and you break it down, you're going to have 128 bits.
Excuse me, sir.
Yeah, go ahead, please.
Can you go back to the previous slide? You broke down the fourth x, the value of the fourth x, into another group of four. Another group of 4
Bit.
bits.
Mm.
Okay. Well, my question now is does that only apply to the fourth?
No,
the X in the fourth position,
no.
or
They
everyone
are
can expand this way?
so we're only using this to explain to you that this
Okay.
one, each of this one,
Okay.
when you pick it, it will give you 16.
Okay, sir.
Is that clear?
Yes, it's clear now.
So it means that what you do for this one, you do for others. It's just a way of trying to show you that 4 hexa and decimal is equals to 16 binary digit. It's not just for this, but for all the hexa. Okay. So once you're able to identify that, then you're good. Then converting between hexadecimal and decimal numbers. So you use the same table to do Baze and Baze. Okay. So there's a quiz. I'll log us to take that quiz. I think we have this number here. So I believe we don't have issue with the conversion of binary to decimal and decimal to binary.
Yes, we have been taking the quiz.
You said?
I said we have been taking the quiz. Yeah, we don't have problem with this.
Oh, lovely.
I didn't take the quiz.
You have not been taking. So you have not been reading. Everything you do, you have a quiz following.
You have a quiz. When you read. At the end, there's a quiz.
I haven't gotten to module 5 in my reading.
No, not module 5.
No, he's just saying, he's talking about the
just saying.
So I want us to quickly, we'll walk through that and then see if, but the truth is that once you understand the table and the conversion, I don't think you have an issue. And that's the beauty about IPv6. IPv6 is just, you don't do much of calculations or manipulations. Rather, you just work with. And then the fourth extent of the IPv6 is your subnet, the subnet map. So, but we'll talk about that. Like I said, before your final exam, I'll deem it fit to take you guys again with the IP address and then possibly with the packet tracer configuration. So we'll take block of IP addresses, we'll subnet them and configure them, and then see the much you can do. Esther, you raised your hand. Is it prior to this time?
Yeah, no, just right now.
Okay, I should pause. Any question?
Yes, I wanted to ask the quiz you talked about. We're not going to take it right now.
No, the quiz is when you're reading and you come to the end of the chapter or the module, then you just answer it yourself. It's just for you to evaluate yourself and see if you're fine. If you're not, then you go back again and read.
Okay, I thought you wanted us to do one right now.
Are we ready to do?
No. Let's continue teaching.
Sir Jesus said no.
Let's teach. Let's continue because we have 17 modules.
Yeah, we have 17 modules. Yeah. We have 17 modules. So data link layer. For data link layer is layer 2. Please note this, that what we're doing here in the OSI, the CCNA1 here is that we're talking more on the layers, the different layers, across from layer 1 to 7. So what we just discussed, I think in module 4 was a physical layer, and then 5 is the binary numbers. Still talking about that we're talking about numbers. The numbers, you can still see them at that level of the physical layer, which is layer 1. And then module 6 here is addressing data link layer, which is layer what? Who can tell me what is data link layer? Which layer is data link layer?
Layer 2.
Layer 2.
Layer 2.
Okay, as layer 2.
Yes. Don't.
So here you need to describe the purpose of the function of the data link layer in preparing communication for transmission on specific media. You compare the characteristics of the media as access control method on LAN 1 and LAN, and then describe the characteristics and function of the data link frame. So like we said, what you have in layer 2 is the frame, and layer 2 is where the error detection is happened. In layer 2 is where you have this, the PDU of your data is in frame. And in this frame, it also to call frame check sequence. So that's where the network, that's the layer the network uses to check for error and do some error correction to see if the bit that arrives at the destination matches what leaves the source. So if what leaves the source, for instance, is 11110000, that's 4 bits of ones and 4 bits of zeros. When it's getting to the destination, the layer 2 will want to check to be sure that the guy that left the source is the same thing with what is coming to the destination. And if it's not the same, he's going to discard it so that it will be regenerated and sent all over again. So that's what we call the frame check sequence. It uses that with the help of the RC, that's redundant check sequence, to check, to match your destination bit with your source bit. So you always note that that's where your error detection and correction happens. So layer 2 is plays a very prominent role in the OSI model. The data link layer is responsible for communication between end devices and network interface card. It allows upper layer protocols to access the physical layer media, encapsulate your layer 3. So what it does is that the layer 2 helps to encapsulate the layer 3, which is in packet, into what? Into frame, and also perform error detection and rejection corrupt. And what? Reject corrupt frames. That means the frame does not match, it's going to reject it. And the data link layer consists of 2 sub-layers. Remember, the data link layer, from what you can see in the picture here, is at layer 2, and beneath the data link layer is the physical layer. But the data link layer has the upper side and the lower side. The upper side is the LLC, which is a logical link control, and the lower side is the media access control. The logical link control actually is the software part of layer 2, while the media access control is the hardware part, where you have your NIC itself, and the MAC address is at the MAC sub-layer. And then, of course, if you look at it, your network layer, which is up here, will interface with the data link layer at the logical link control. So this is like software-based and hardware-based. Please, I want us to note that, very important. So the MAC sub, if you look at what we have, the LLC sub-layer communicates between the networking software at the upper layers and the device hardware at the lower layer. So your MAC sub-layer is responsible for the data encapsulation and media access control. So you need to note that, very important. If you look at it here, it's telling you, if you look at this what the IEEE came up with is that at the MAC sub-layer, you have 8.3, 8.11, 8.15. That tells you, somebody asks you which part of the data link layer is responsible for your Bluetooth connection. It's at the MAC sub-layer and not on the LLC sub-layer. And then the 8.11, which is the Wi-Fi, actually takes place at the MAC sub-layer. And then same thing to the Ethernet. So we need to note this. One minute, please. Okay, so let's see. But I want to believe everybody has their packet tracer installed.
Yes.
Okay. When you're doing the model 1, the packet tracer pop up?
Yes.
Yes.
So I think you don't have.
Esther, you are not done with the work.
I started a system test. system assessment test. And my packet tracer was automatically opened.
Okay.
Okay.
Yeah.
Okay, that's what I want to know. So the data link layer protocol are defined by the engineering organization. So these are the bodies that actually helps to regulate the data link layer, which is layer 2. Because what I'm asking is that so you note down this that when you'll be doing your configurations, your packet tracer does not pop up. Those questions that you're meant to answer on the packet tracer, you might lose those marks. So there's a need for you to follow the procedure to be sure that it's working. Please, this is important. So that when we're doing the final lab for this CCNA1, you'll be able to do that without issues. So there's need to test all of that because what you're doing is more or less like practice model exams. The final exam is actually the main thing. That's what really ascertain your grade. So if you're going to pass, that's where you really know. And then when you have issues, so please, you need to test your packet tracer to be sure that you don't have issues with that. So we've talked about physical topology and logical topology before now. We said when it is physically connected, it is physical topology, and when it's configured with MAC or IP address, it is logical topology. So there are 3 main common physical WAN topologies. It's either you're doing point-to-point or hub and spoke or mesh. When we say hub and spoke, we're looking at similar to a star topology, where you have one network at the middle and every other guy is connected to it. That's what we call the hub and the spoke. For instance, you have Baze University. Baze University has NOC in maybe the main campus, and then maybe you have other campuses. Then you can, the other one will now be like the spoke. Like for instance, in Uniport, we have 3 campuses. We have the main campus, which is an Abuja campus. We have a place called Abuja campus. It's not your own Abuja. And then we have Delta, we have Choba, and then actually Abuja campus inclusive makes it 3 campuses. But for instance, the main campus, where is the permanent site, is the Abuja campus. So you now have these other 2 campuses, you know. So if the NOC is actually stationed in Abuja campus, and there's connection from Abuja campus to Delta and Choba campus, we can now say the Delta and Choba campus are the spoke, while Abuja campus is the hub. I hope you get what I'm saying.
Yes.
Yeah, so that's what it means by hub and spoke. So it means that the main network is actually at the middle and is connecting to other, just like a company that's in Lagos and have a branch in Abuja, have a branch in Port Harcourt, and have a branch in Lagos, for instance. So it means that that company that's in Abuja will say their hub is in Abuja, while the spoke is in the other part of the country. So the one at the middle is the hub. So this is what this is the kind of network you see, and most of the configurations you might be doing subsequently might actually be around the hub and the spoke. So for the mesh, it provides high availability and but requires every end systems to be connected. So for the hub, for the mesh case is like when you have a branch in Abuja, and then from Abuja to Lagos, from Lagos to, and then that's what Abuja is the hub in this case. And then a branch in Lagos, a branch in Kano, a branch in Port Harcourt, a branch somewhere in where else? So if when you connect Lagos, for instance, to Kano, you connect Kano to Port Harcourt, that is mesh. That means even the spoke, you're now connecting the spoke to the other spokes. And the reason why you're connecting it is so that you now bring them back to the hub. So it provides a very high availability because if one part is down, the other part will provide access. So let's say, for instance, if Lagos is connected to Port Harcourt and Port Harcourt to Abuja and Abuja to Lagos, if the link connecting Abuja to Lagos is down, as long as Port Harcourt is connected to Lagos in the other connection, you're sure that Lagos will still be up because it provides redundancy, some kind of backup connection. So that's where the mesh comes in. So mesh is actually very good because it helps to increase availability. So this is a point-to-point connection where you have two end systems like this, one here and the other one at the other point. Okay, and then this is bus star topology. You can see the star topology. You can see extended star topology, and then bus topology, and then ring topology. So here in the bus topology, all end systems chain together and terminate on each end. Okay, and then for the ring, you can see the ring. Each end system is connected to its representative neighbors to form a ring, as the case may be here. Okay, so for half duplex and full duplex, allows one device to send or receive at a time. I've explained this before, but this is when we talk about duplex communication. That's topologist communication. So topology can communicate as half or as full. If it's half, it means that when one device is sending, the others will be waiting, and then once the line is available, others can now send. This is the case of a hub connection. So when I say hub, I'm referring to a hub as a device, okay? Not HOP, but rather hub, HUB. So full duplex. How many of us have seen a hub before?
Yes, sir.
For switch, we used to have hub.
Yeah.
The hub is actually operating on layer 1. The hub does not interpret signals, it just propagates the signals. So whatever it receives is what it just sends, like a wire. So it does not interpret the signal you have. That's the reason why you have high collision on the hub. So I'm saying that the hub here is a half duplex. So that's why when you have more than maybe 5, 10 systems or 15 systems connected to a hub device, you end up having collision because the hub is not able to manage, does not have that intelligence to be able to coordinate that signal. So but for full duplex communication, it allows both devices to simultaneously transmit and receive on a shared medium. So your Ethernet switches operate in full duplex mode. Please, you need to note that, please. And then we have the access constraint method. We have what we call the CSMA-CD and then the CE. In the case of the CSMA-CD, is the carrier sense multiple access collision detection used on legacy bus topology Ethernet. When we say legacy, we're talking about your old hub system, where once there's a collision, everybody will wait, and then once the way is free, then the other person can send. But for the carrier sense multiple access with collision avoidance, this is used in the case of wireless. So we're looking at how frame or data packet is being transmitted in the case, but remember here we're talking about layer 2. And so you're also looking at it from that angle of you waiting to, when you want to send, when system A is sending, system B will be able to wait. That's a case of a detection, but for avoidance, it's a case where both can still send at the same time. That's why in your wireless network, you can do normal sending and receiving of data signals without much collision. But what we're saying is that it's still possible. So all nodes operating in half duplex competing for use of medium. So they compete for that medium in the bid of trying to send and receive signals at the same time. So the control access means the domestic access where each node has its own time on the medium. So used on legacy networks such as token ring and ArcNet. When we say legacy, we're talking about old forms of devices or old equipment that are used for data transmission. So the CSMA-CD used by legacy Ethernet LAN operating half duplex mode use a collision detection process to govern when a device can send and when you have and what happens if multiple devices send at the same time. The CSMA-CD collision detection process, devices transmitting simultaneously will result in a signal collision on the shared media. Devices detect the collision, and devices wait a random period of time and retransmit under the CSNA CD. There's bound to be collision, but when there's collision, you have to wait. So it's like a timer that tells, okay, fine, it's free, you can move, and all of that. So the data frame. So here is the frame. So data is encapsulated by the data link layer with a header and a trailer to form a frame. So you have your frame in your data. When we say frame, a frame is actually a packet in between and a header and a trailer. So when you hear frame, don't think frame is different from packet. It's the same thing, but just that when it's getting to the layer 2, which is data link layer, it's going to add some kind of identification at the top, which is the header, and it will have another one at the end, which is a trailer. So the header is like when it's pointing up to layer 3, the header is up and the trailer is down. The trailer now is pointing to layer 1, while the header is pointing to layer 3. So what we're saying is that that identification that add up to the frame, and sorry, to the packet, is what is referred to as a frame. So the entire length of the packet, when you have a trailer and a header added to it, is a frame. So it is still data that is changing from one form to the other, but it's changing with some form of identification. It's just like a runner who is, there's this, how do you call it? And those people who actually run around the field. One person is running at one point in time, and then they pass on the baton to the next person. Am I correct?
Yes.
Okay, now when he's passing the baton to the other person, you see one hand is at the back and the other hand is at the front. So now if you look at it invariably, you discover that these are still individuals who are running and they are passing on this baton to the next person. So that baton they are passing to the next person that is moving from one point until it gets to the destination you can see it as your data. Yes, that's your data. But just that your data is changing form from one person to the other, because in the whole race, you're not going to have the baton move from point A to point B. The baton must pass from one individual to the other. That's exactly what's happening in the website layer. So when that data is moving, it's going to carry a header and carry a trailer. That means when the man is putting his hand behind, he's putting his hand forward to pass on that person. We're saying that extension, both at the back and at the front, add to the entire data, which is the individual who is carrying it. So we are now saying that addition at the head and at the trail is what changed in form, which is the encapsulation process. So when it gets to any layer, it has a new name. In the case of a data link layer, it becomes a frame. So, but when you remove the header and the trailer, what you have here is a data in between them. So we're saying that the data is encapsulated by a data link layer with a header and a trailer to form a frame. So a data link layer frame has 3 parts: header, data, and trailer. Okay, so the feeds of the data of the header and the trailer vary according to data link layer protocol. So the amount of control information carried in the frame varies according to access control information and logical topology. So based on the topology as well. So but what you should note here is that you have the header and the trailer, and then what does the header do? It's more or less like a checksum. It helps to check to the next layer. So if you look at this is like the architecture of a frame. So you agree with me that you see the header here and see the data here. In this case, data here is packet, but you can see in bracket we wrote here data is packet. But what should be your concern is that the length of this header to this trailer is the frame, and which is the encapsulation. So something is encapsulated, and what is encapsulated is the header and the trailer. So this is actually the architecture of a typical frame, telling you that the frame start and stop, when you to start and stop when you're sending, and when you to stop because of transmission, and then the addressing, the type, which is identifying encapsulation layer 3 protocols. So all these are just a way to tell you what the frame is doing. So the control E service to identify the flow control service. That's from the point when it's sending to when it will be received. And of course, data contains the frame payload, which is itself the packet. And then the error detection used to determine transmission errors. So like I said, the error detection here is to detect for errors. So it's the data link layer that detects your error. But the layer, the transport layer, which is layer 4, does what we call error detection, sorry, what we call error data integrity. So your layer 4 helps you to maintain the integrity of your data in the course of transmission. But one thing that helps to detect the error itself is layer 2. And like I said earlier, it uses the frame check sequence. So when you be reading the curriculum, you come across it certainly. And please, when you get there, take your time and understand that area, because that is what it uses to check when there's error. There's no calculation there. It's just to look at the variation in the bit. Layer 2 addresses, also referred to as a physical address. It's contained in the frame header, used for local delivery of a frame to the link, updated by each device that forwards the frame. That's layer 2 addresses. And the layer 2 address is your MAC address. Please, you need to note that. So your LAN and WAN frames. So the logical topology and physical media determine the data link layer protocol. Because when we say the WAN, we're talking about the wide area network. And when we talk about the LAN, the local area network. So the protocol uses the Ethernet. So these are the technologies or the protocol that you have under this data link layer for LAN and WAN. Remember, we know what Ethernet is. Ethernet is that port in your switch, in your system that enable cable connectivity. And then the 802.11 wireless actually uses the same Ethernet port. Note that your wireless will not work until you connect either a cable to it from one point. So when you see a wireless network, go and check. There's some kind of LAN connection somewhere that aids that connection. So point-to-point connection, then high-level data link control, and then frame relay. These are all the protocol. These are all protocols used under your data link. That's your LAN and WAN frames. So each protocol performs media access control for specified logical topologies. So what you do is that when you, like I said, when you read through all this, you take your time, you go back again, look at your objective. Be sure that you have met the objective. And what is it? Is to describe the purpose and function of data link layer in preparing communication for transmission on specific media. And when you're explaining this, that is where you have to sit down to explain the CSMA CD and the CSMA CE. Because when you describe the function of the data link layer, telling us where it is, which is layer 2, and then it has a header and a trailer, it does error detection, it also have half and full duplex, and for the half duplex, it operates under the CSMA CA and the CD, and then you explain each of them, and you also tell us which devices are found in each of this category I've just mentioned. Then you're good with that. And then you now compare the characteristics of the media access control method on the WAN and the LAN topologies, which we listed out. As your frame relay, we listed out your Ethernet. Now, all those protocols, they still fall under the same LAN and WAN topology. So you also need to look at them and then describe the characteristics and function of the data link layer. What are the functions of the data link layer? What do they help you to achieve? So once you're able to do that, then you're good. Remember, when you're explaining this, you could see that the data link layer itself has two sides. It has the software part and the hardware side. The software part, which is the LSC, and then the hardware side, which is the MAC, which is the media access control. And then you should really let us understand that the LSC part is the software, and then this part is the hardware. The software is the part of the layer 2, which actually interact with the layer 3, which is the network layer. So if you're able to put that together, so in summary, your students, you should be able to summarize a breakdown of what the entire module here is talking about, so that they end up getting the objective. So this is where the review comes in. So what we do in Cisco is that when you finish teaching, you come back sometime, most cases, to the objective and ask the students, at this level, can you explain this? They explain. At that level, can you explain it? If they're able to make a justification in whatever you've explained, then that tells you that that is taken. If they're not able to explain it, then you have to go back again and then explain that. For instructors, it comes like a crash course for you. But when you're teaching your student, please, we're not expecting you to crash it. It should run like in the whole semester for them. So if you have a semester of maybe 12 weeks, 14 weeks, fine, then they go along with it. So you enroll them even before they resume that semester, let them have access to the curriculum, they start reading, and then when you resume, you make it one step at a time for them. And I bet you once they go through the academy, they will enjoy it more than just going to read one certification exam and write maybe DOMs and the rest of them, because the essence of all this is for them to really have a clear understanding of what we're talking on that communication here. And for folks in those fields, I think it's another way of bridging their knowledge. Okay, so far, this is all we have for this module, and I think 4, 5, 6 has been taken. I'm going to pause here. In case you have questions, you can ask, and then we'll move on. So this is 4 already. So this will go for prayer. We'll go for prayer. Any question, please? Any question?
Well, no question, but just comment.
Okay, comment. Okay, thank you.
Yeah, we appreciate the sacrifice and the explanations, which are quite comprehensive. And we thank you for sending the PowerPoint materials so that we can read ahead. One thing I discover is that because some expressions or terms used are really specific to Cisco and not global as such, although Cisco dominates the market. So we need enough time actually to go over and over to get clear understanding of terms as used by Cisco. But otherwise, it's very interesting and we enjoy it. So thank you very much.
Okay, thank you, Dr. Barrow, for that contribution and that input. I think I understand what you're saying. This is like Cisco. But then as also in the academia system, the good thing is that you, like you said, you already have the curriculum with you. So the instructors now can now make justice to the curriculum. Yes. When I say justice, I mean you now look at it and try to make it holistic and then look at it from there. But the good thing is that with the Cisco is that it's practical oriented. So it gives a clear direction, so it's like, and that's what we do. Like I was telling you in the last time I came to Abuja, is that in other institutions, what they do is that after teaching a particular part of communication, you will now say, okay, for example, in Cisco, this is what it is. So let's dive into this so that you do the hands-on, you learn this and then apply it so that this is the environment. So in case tomorrow you find yourself in another, maybe Huawei or something, or you have find yourself in another environment, you always know that this protocol remain the same. The only thing that will vary is probably the command, 1 or 2 changes, but then the protocol, this order of steps that must be followed, it's still the same thing. It's not going to change. And then the standard, like the OSI model, is a standard. Cisco cannot deviate from it. So also the other vendors cannot. So it's going to be like a vendor-based thing. So like this is Cisco own. Other vendors might have their own, but at the end of the day, they still have to be in the same They still have to respect the industry standard.
Yeah.
So I think the instructors now have this to make justice to it, to go along with. So thank you very much.
Thank you.
That as well.
When
So
is our
Julius,
next meeting,
okay.
sir?
Yeah, thank you. So Julius is not there.
Hello, sir.
Okay. So I'll send the recording immediately, please, alongside with the previous one, so that for the weekend, I know you have Saturday, Sunday to go through all of this and then read ahead. So what I will do by Sunday, I'll equally send for, I think I've sent up to 9. So I'll now send 10, 11, 12. So I'll make sure I send that as well, so that those of you who are already running up this one can take up the other one as well. So it means that you need to take this quiz, sorry, this end of module exam for 4, 5, 6 within this weekend.
Yeah.
And the reason why we're doing this place is because as we're running up, we're sure we're good to go. I wouldn't want people to have backlog of module exams. So that's the reason why I'm trying to see that we go alongside. If not, before you know, you have so many exams. Right?
That's right.
And please, the lab is very, very important. Like I said, in subsequent classes, I'll take 1 hour for labs. The lab exam you're going to do, I will set the lab exams and I'll configure in such a way that you have maybe 1 hour, 2 hours for the exam. And we take lab to be like 60% or so. So you need to take the lab seriously, because at the end of the day, you as instructors, what the student really hold, value a lot is the lab activity. Students love doing practice. So I want to see how your teaching should be centered more on practical than the theory. And so you give them a lot of lab activities to do, topologies to configure. I mean, they are so excited doing this. But when you tell them to explain certain theories and concepts, they get so, they get so bored with that often. But then when you mix it up with the lab, so that means you as instructors, I'm going to actually make sure that you have number of labs to do, and your final assessment will be rated more on the labs rather than the theory. So please, I want you to go back again to the packet tracer and do a lot of practicing. Of course, we haven't done any configuration so far, just basic management configuration. But I can assure you in the coming week, you have a lot of labs to do.
But there are labs. In some of the.
Okay. If there are no questions or contributions, so am I permitted to end the class?
There are some labs at the end of.
Mr. Makinde is talking.
Julius is trying to say something.
Okay, I'm not even hearing him. Well, it seems it's far from you.
Julius, your voice is low.
Okay, maybe I reduce the something. I say the labs that are there, I will encourage us to take it.
Yes.
Yeah, there are labs. If you go to your student resources or you see student lab, just download them and start practicing them to go a long way. And then over the weekend, I'll try and get some labs and send. Possibly tomorrow by God's grace, some of the labs that you just need to, on your own scenarios, that will tell you on a position A, have this and that, you're asked to do the following configuration. But please, when you see those labs, don't get worried. Do the much you can do. If you can't be able to do it, then I will take them one after the other as we go on. I'll do it myself so that you don't, there'll be no cause for panic.
Nice that we try to lay our hands on them.
Thank you very much.
Thank you so much, Dr. Barrow.
Thank you. We are grateful.
Sir Julius, you seem to be far from the mic. I don't know if I'm the only one experiencing.
Maybe it's I'm using my tab. Maybe it's my tab.
Okay. Okay.
Yeah. Okay. I know what happened. I was using, don't mind me. Okay. So can you hear me now?
Yeah, better. This is better.
Okay. It's okay. So it will be nice if you send them. We'll be able to.
Yes, I will. I'll do that.
Okay. Thank you so much.
Okay.
Bye. Now, students, you are taking what do you call it? Attendance. Your attendance is 30%.
Please, attendance is very important too, because when we're doing all these labs now, I wonder if those who are not attending, by the time you now give them exam, I wonder how they'll cope. Probably some of you have done this before. So, but then
maybe
the thing
they've
is that
done it
even though you have done it before, the instructor can change the lab. I mean, he has a
Yeah.
right to give you any design and
Mm.
tell you what he or she wants. That's why when you become instructor and you're teaching your students, just leave them. They can go and do anything. You come and change your configuration. Tell them what you want. Change the IP scheme. You know, tell them which one you want to be the first usable, which one you want to be the last. Change the subnet map. And before you know, they get confused. Reason being, as well, they can be in class and learn from the instructor.
Yeah.
They don't believe that because they have one DOMS or one materials that explain everything. They don't need you. So you are the one now to change the part. So by the time they see that you're already doing that, nobody will tell them. They'll sit in the class. Okay, sir. So thank you very much, everyone.
Thank you.
And have a lovely weekend.